Hi everyone, this is ME 5390 Advanced Thermal Design. Today is Monday. Last week I had some lot of family stops to resolve. Anyhow, I come back. I'm going to continue chapter 4. Okay, chapter 4, compact heat exchanger. Yeah. You had some homework problem, and you might have some questions probably in advance. So I'm gonna go quite detailed. So you will see. Okay, mostly I hope you solve the question problem. Yeah. So compact heat exchanger chapter 4. I'm using my file. So page numbers are a little different with the books. I have to use a PDF. I tried to get the PDF from the book. It is costly, each chapter is $45. So I couldn't buy it. Some of them I bought, especially chapter 4, I couldn't. Okay, so I use my file. The contents are the same, but page numbers. Okay. The first of all, I like to indicate surface. Surface area density. This is we are using to indicate how compact. Okay. So the unit are meter square divided by volume. Okay, meter square is area, heat transfer area actually, divided by volume. So that the compactness we can indicate, say beta. Okay, whenever we design heat exchanger, the compactness is important. How compact? Okay. It's not necessarily small. Small is depend on the heat rate, but the compact density is somewhat important. Compactness. Okay. I think first of all, the heat exchanger we discuss two things. Okay. Let me see. Rating, and the size. Okay. So the rating is heat transfer rate, pressure drop, something like that. Okay. And then size is size-wise dimensions. Okay. Practically, size is important, but complicated and difficult to figure out the size. So most of the book, heat exchanger, they mostly talk about the rating, pressure drop, heat rate change of heat or heat transfer. But in this chapter, we discussed the size. You will see that, okay? It's very time consuming sometimes. So, but but we have to understand what is size. Okay, and when we compute the surface area density, 600 is compactness. Okay, so smaller than 600 is compact. It's directly related to hydraulic diameter. So we can also have a expression or index of a hydraulic diameter. Okay, so something like that. It turns out about 6 millimeter. Smaller than 6 millimeter is compact. Okay, now the type of heat exchangers, there are a number of types, but the fundamental, okay, the fundamental is a double pipe heat exchanger. So very simple. This is just a pipe, but concentric pipe, and tubular floor and annulus flow, simple. But that is a fundamental we develop. So then we compare the other type with this fundamental. So it's easy, but basically same discussion. Okay. Another type is shell and tube. More 80% of heat exchanger shell and tube, very durable, strong, and easy, clean. So it's not really compact, but typical. So basically, we discuss everything, not only compact. Double pipe, shell and tube. Okay. And this type is a very historically 100 years well-developed design. I think more than 75, I think 75% market share, and temperature-wise, pressure-wise. But also we can look at compact. Yes, small. Okay. So some schematic drawing, double pipe, shell and tube. Shell and tube is a tubular flow and shell flow. Okay, something we will discuss. And C is plate, typical, very typical. You can see this type anywhere, swimming pools, heating, because of compact and small. So rather than this shell and tube, they prefer this type. They call plate heat exchanger. There's a braze type, other type. And then circular finned tube heat exchanger. This is a very typical air conditioning, automotive radiator. Every air conditioning system, because of one fluid is air, the other is the fluid. So in that case, the different heat transfer features, typically, yeah, this is the type. And then the gas and gas, air or gas, is very compact. This is most compact heat exchanger. Probably can discuss this. So plate heat exchanger, P, and plate heat exchanger, and um, yeah. Well, anyhow, yeah, I showed. Again, yes, rating and sizing I discussed. Okay, so let's look at the fundamental. It probably you can think of double pipe, but not necessarily double pipe. Okay, the basic fundamental features, counterflow and parallel flow. Let's look at it. So it could be double pipe, but not necessary. Okay, as long as one cold fluid and hot fluid, counterflow, counterflow, and mass flow rate 1 and 2, temperature 1, inlet T1 inlet, T1 outlet, T2 inlet, T2 outlet, so that we can indicate the inlet outlet, fluid 1, fluid 2. But keep in mind, once you are in the middle of computation, very complicated. Fluid 1, fluid, which one is which? If you mess up, it's a disaster. Okay. So what I did in this textbook, 1, this is 2, is hot. 2 is cold, relatively. Actually, 1 is hot, the other is cold. Okay, so always put hotter into 1, subscribe 1. Okay, and then easily you can. It could be gas, it could be fluid. It doesn't matter. Hot and cold. So number 1 is hot. The I is inlet, O is outlet, so that easily you can distinguish. And then temperature and length. Which one is the highest? Can you participate answering here? Which one is the highest in this heat exchanger? Highest temperature using the symbol. Answer.
T1I.
Yes, T1I is the highest. Left or right? You can see from direction, left or right. Well, this is right, this is left. That's just simple things. Left or right? Come on.
Left.
Left, yes. So this is T1I left, which is the coldest. Which is the coldest?
T2I.
Yes, yes, say T2I. And then T1I is highest. This must be decrease. Okay, so T1I. T2I is also, it should be increased, something like that. Okay, I don't know, but something like that. And then direction, flow, okay? And M1, hot, M2, maybe CP1, CP2, depend on the fluid. So we can draw distribution is important. As long as you have a heat exchanger, you can draw distribution. It gotta be counterflow. Okay, and the wall temperature is it gotta be in the middle, the wall between. This is wall. Okay, now and once we have distribution, we define delta T1 is difference. Little don't confuse this 1 and 2 I'm using is not subscript hot and cold. The left side is 1, right side is 2. So difference T1I minus T2 not. Delta T2 is T1 out minus T2I. Okay, so whenever you have a distribution, always T1, T2 you can define with the, you can, okay, no question, but you have to draw distribution. Okay, now parallel flow, okay. So T1I, T2 out, T2I, T2 out, and what is the highest, which is left, which is coldest, which is left. That's why left to right, and then it's increasing. Okay, increasing. So that again, delta T1 is difference, delta T2 is difference, delta T1, delta T2 is defined, as long as you have distribution. So you don't have to remember, actually. I don't never remember equation, delta T1, delta T2, parallel, okay? Always I draw distribution and you got it. You have to follow it. Don't confuse. And then interesting, the wall temperature gotta be average in the middle. So that's sometimes we need the temperature of wall temperature. So, but this one counterflow is average. So is along with the temperature decreasing. The nature of parallel flow is just horizontal, something like that. Okay, there's sometimes we need to know the wall temperature. Mostly we don't need the wall temperature, but some fluid like exhaust gas, we want to avoid what is condensation. Okay, so the temperature is important. So in that case, maybe we need wall temperature. Otherwise, we don't need. This is very special case. Uh, I mean, the dew point uh, matter sometimes. um, so when we look at the cold side, hot side, hot side is the heat transfer must be outside, outside, which is inlet temperature outside. Anyone? Highest? T1I is the highest. And what would be heat transfer enthalpy flow? Anyone? Q. So in this case, the heat transfer enthalpy flow m dot Cp, whatever highest temperature, if T1 is higher than T2, then T1 minus T2, and this is plus out. So what is the temperature is T1 out and plus. Now cold is anyone figure out? M dot 2 CP2 T2. Which one come first? In order to be plus, out, because coldest is a T2. I is coldest. Do you understand? So that you can say that. We like to have always positive here. So that's the what we have here equation, and we will discuss more that we have one more equations overall. 1, 2, 3 overall is again Q is now we will discuss UA. F is depend on the type, and then logomean we'll talk about more later, but we have equations. So as long as we have a logomean, temperature difference, and UA value and F. This F is a correction factor depending on the type of heat exchanger. Okay, so double pipe, F is 1. Keep in mind, I'm telling you. Shellenshu, F is something we have to look at it. So depend on the type. But double pipe is 1. Okay, so if we talk about the double pipe, it's just the UA logomean temperature difference. Okay, and the logomean is defined easily. Logomean is delta T1 minus delta T2 natural log delta T1 over delta T2. You don't have to remember, easy. All remember is natural log and first come first, that's it. So this is we will derive later, but at this moment we just use it. So what is U overall? U is overall heat transfer coefficient, convection coefficient, but there are two fluid, so we use overall. And delta T1, delta T2, we never ever remember. I don't know. Okay, so figure distribution. And U is overall, A is heat transfer. So if it is a hot side, multiply is UA. Cold side is we call E2. Okay, cold side heat transfer area. It turns out it's the same. Interesting. So it's weird, but so sometimes they say UA. It doesn't matter, one or two. Okay, so this is probably you better remember without the proof, it turns out. Okay, so some analysis. And A is a perimeter times length, you know. The perimeter times length. This is perimeter, something like that. So now overall heat transfer is something complicated. Look at that. Fluid, cold, hot, two fluid. And there's walls, depend on the type of walls, plate or cylindrical, whatever. So I say H1A1, I can say that. And then cold side H2A2. So that we can construct the thermal circuit T1, T2. So from T1, T2, we can construct there is a heat flow Q, we know that. And this is the wall. This is a wall. Depend on the type of wall, plate or circular. But the convection is, we know that, 1 over H1A1. Convection, the resistance, convection resistance. So if in that case, we can construct the total resistance between these two is sum over resistance. Look at that, sum over resistance. But this temperature is very complicated. Keep changing from inlet to outlet, outlet to inlet. That take care of log mean. Wow, that's the power of theory, theoretically. F is nothing, is a type of heat exchanger. So log mean is take care of all this complicate, keep changing, but resistance is the same. That's why we can construct UA 2 or UA. Okay, I said the UA is the same. And this is a plate. We know heat transfer. If it is a plate, then thermal resistance. If it is a cylinder, This is a cylindrical thermal resistance. So we can handle both. But sometimes I said UA. Don't ask me which side. No, you can go any side. U1, A1, U2, A2. Okay? Whatever you call convenience, you can do that. Or U0, A0, whatever. Actually, out is outside, I is inside, whatever. Okay? So just UA multiple product is the same. But I don't want to use this, but if you divide by U2, something like that, look at that. You can even compute U2. Did you see that? If you calculate these, and then A2, you can calculate U2 if you want U2 overall. So even you can calculate U1 because A1 of U2, A2, isn't it? So whatever you can calculate. Example, you can look at it. Now log mean temperature is, I'm not going to go detail, it's beyond the scope, but it turns out we can derive, yes, I told you, we derive log mean. So use it. And the hydraulic diameter, sometimes hydraulic diameter is defined AC over P, perimeter, wetting. Keep in mind. So, for example, square, circular, you don't have to calculate the diameter. Circular diameter is a hydraulic diameter. But this one, you can non-circular, you can compute the hydraulic diameter using this. Or annulus, small, large, then hydraulic diameter is 4 AC cross flow area. You can calculate, no problem. But the perimeter is large plus small perimeter, 2. You have to add up. And here in heat exchanger, they use a mass velocity. So the mass velocity is nothing more than density times velocity, mean velocity usually. Because the velocity is complicated. Flow, the fully developed flow velocity is something parabolic. So it's complicated, but if you use mean, T mean, or velocity mean, okay, velocity mean, not velocity mean is you can calculate. So you use a mean velocity. Anyhow, the mass velocity sometimes in this book, in society. So we have to use, usually mass flow rate is density, velocity, and the cross flow area, but also you can use GAC, because of this mass value. Reynolds number again, GU, but in terms of m dot or in terms of G, so don't confuse. This is original in terms of m dot, in terms of Z. Okay. Sometimes they use equivalent diameter. So what is the equivalent diameter is a perimeter, not the wetted, heated perimeter. So annulus heat transfer is insulated, for example. So what is the hydraulic diameter is for AC is no problem, you know, the flow area. But now perimeter is which one? Is it small and larger one? Do you think? Not the hydraulic, but equivalent diameter. There are two, large and small. Which one are you going to take it? Because heated, the small one, not take a larger one. Okay? So small one, because only heated perimeter. That's the, so why? Don't ask me why. They had the difficulty to predict, and they had to use equivalent diameter sometimes in heat transfer. So there are two, hydraulic and equivalent, and then you have to use the definition. Equivalent. Hydraulic is a hydraulic. For example, Nusselt number, laminar flow, they use DOBE equivalent. Then you have to use equivalent. Okay, this is a convection coefficient, and K of F. What do you think of K of F? Anyone? Answer. What is a K of F? Do you think?
It's the fluid's heat transfer coefficient, or not heat transfer, but conductivity, thermal conductivity of the fluid.
Yes, yes. You have to say exact terminology. Okay. Thermal conductivity of fluid. Okay. Yes. Gotta know that. And turbulent, we suggest.
So
But
what about the mu sub s?
Sorry. This is complicated. Is the surface. Usually we use a film temperature property, but this is complicated. They use surface temperature. In this course, U over US 1. Okay, in this course, don't bother with. We don't know even wall temperature. Do you understand? Yes or no?
Yeah,
Yeah,
I tried doing it in my homework and I
just
didn't.
one. Yeah,
Well, I turned it in already, but it was close to one.
yeah. Just use one. Don't bother. Okay. Actually, we don't know. Yeah, we have to assume it. Now, Nusselt number for turbulent, we have to use Reynolds number, Prandtl number, and F, friction factor. So is given. You have to use for turbulent. Oh, this is important now. Effective. This is so important. Wake up, everybody. Okay, you got to understand this. effective NTU method. People are saying LMTD method. And the effective NTU method. Two methods you can solve actually, because this is analytically you can solve it, but the industry, they prefer use effectiveness NTU method. And also I prefer, because effectiveness. Why? When we talk about heat exchanger, the LMTD method, no way we can compare the heat exchanger. Even type, we cannot compare until we calculate the heat transfer rate. Sometimes the heat transfer rate is depend on the size, not the really performance of the heat exchanger. So effectiveness method gives us effectiveness, like efficiency, something like efficiency, not exactly, but so we can see how good it is. That's the big difference when we are considering which type. Then it's hard to compare. It works. Every heat exchanger type, it works. But which one is the best? So that this is good effectiveness. That's why we are the Professor Kayes and London's Stanford, I think in 1950, they developed this, and since then it is good, real good. Okay, so here Kayes and London, 1955, yeah, 1955. So what is this type? I think if we can define what would be practical max heat transfer, that was a very challenging. What is the maximum possible? Not the maximum possible, practically possible. Okay.
Here's what I found.
Here's I found what? Who is saying that? Computer saying that. Okay, now, so we're gonna define let's say m dot, okay, the hot the product mass flow rate and specific heat is capacitance. If you product, okay, the capacitance of hot fluid, and this one is hot, cold fluid, compare. So if the hot capacitance is larger than much larger, for example, much larger, okay, than the cold, then what happened when we draw the distribution? This is the hottest, this is the coldest. Which one is really dominate because of the capacitance, like a semi-truck and a small car, something like that, because of capacitance. So what happened is the cold capacitance is just a steady, and then hot small car capacitance, it is following the tendency, okay, because of capacitance. If it is the same, if the capacitance are same, something like that, but the cold is higher capacitance, then it's gonna move. So this is the trend, is moving. So this is the case. The other case, if the cold side is a cold side, capacitance is much higher, then look at that. Hot side, cold side, hot side is gonna move. Something like that. So if this is the case, what would be maximum heat transfer? Can you figure out? I think you should figure out what would be practically maximum. Maximum could be very high, impractical. The matter is still we're gonna use m dot Cp and the temperature difference. Okay, so
It's m dot Cp of the smaller one times T1 n minus T2 n.
n, what is the n?
N, I.
I is not n. I is I. Why you say?
I said in, like as in and out. In.
Yeah, in. I.
Yeah.
Not the
In.
n. Yeah, in. I'm sorry.
Right, right. I was just wondering, like, if one of the CPs are unknown, is there a way to tell that from the temperature
So
difference?
yeah, what would be temperature maximum possible temperature difference?
Minus T2I.
Uh, yeah. Yes. Thank you. You're right. This is actually Cage and London figure out. Not the max one. Max is not moving. Min is moving. You see that? So once you figure out then effectiveness is Q max over Q actual. That is effectiveness. So effectiveness is now Q max is m dot Cp, whatever mean, smaller one, times T1I minus T2I. Gotta be.
So
And then
there's no way to tell which one's the smaller one from the temperature difference?
if we know,
Okay, if we know the temperature difference?
yeah.
Because I think one of the homework problems, it just said it was a gas. It didn't say what type of gas. So I didn't know how to specify it.
No. You should know the inlet. Inlet is usually no. We know that.
Okay.
Inlet is usually no question, no optimum, no nothing. Inlet is inlet. It should be there. You got it?
Yes.
So we know the max. We know the max. And then Q actual is there are two, hot side and cold side. That's very interesting. This is one is a hot side or cold side. One,
Hot side.
yes, this is a hot side. Two is a cold side. There are two. So this is known, and m dot inlet is known. Do you think you can calculate the outlet if you know the effectiveness? if, do you think you can calculate the outlet? Yes or no?
Yes.
Yeah, that's the key. You can figure out the outlet if you know the effectiveness. Okay, that's the NTU. How to calculate effectiveness is, they say, effectiveness is depending on the, look at that, counterflow, we found it. Parallel flow, we found it. Where is the parallel flow? I think parallel flow, we found it. And whatever, analytically, we can find cross flow, we found it. So look at that. I'm not gonna demonstrate, but we found it. So once we know the effectiveness, but what we need is the CR and the NTU. What is the CR? Anyone? What is it? Do you remember? Is U not anything, and M dot CP mean you have to compare two. So CR is you have to compute the UA and M dot CP mean. Then CR is no. I'm sorry. This is NTU. NTU. CR is just M dot CP mean over M dot CP max. So CR is less than 1, greater than 0. Okay, ratio, CR. The NTU is you need U or UA. You have to work on that. So once you have U or A, UA, then you know the NTU, you know the CR, then you know the effectiveness, then you know the outlet temperature. Okay, something like that. This is one way using the effectiveness. The good thing is this is the value. How effectiveness of the heat exchanger? 0.3, 0.5, 0.7, good value. Because Q max is a maximum possible, so it is a meaningful. When you design heat exchanger, it is a 0.01, no good, no good. 0.3, it depends on the type, maybe, which is highest. I think my understanding is 0.85, highest in the world. Because the money, effectiveness is money for power plant. Per years, billion dollar difference depending on the effectiveness. Okay, so important. And the cross type is a little complicated, but the theory, actually, this is a beautiful theory. So smart. People are so smart once you understand. So it doesn't matter what type, as long as the cross, it works. It's amazing. Amazing. Even counterflow, is really doesn't matter. Any type is counterflow effectiveness equation is there. So powerful. Somebody designed a very complicated heat exchanger effective. But you look at counterflow, beam, you can calculate. Crossflow, beam, you can calculate effectiveness. So I'm not going to go and detail derivation. If you have time, you can go and look at it. It takes an hour to go over. And we found the effectiveness. That's it. Still, I'm using NTU, same UA, C mean. C is capacitance, C mean. So once you have C1, C2, you have to compute which one is the C mean. And one more things. Actually, it depends on the mixed, unmixed. Okay, so look at it. This is something like separated. Okay, the flow coming. Is this, do you think, mixed or unmixed fluid? Tell me.
Unmixed.
Unmixed, because this flow is go out. This flow is go out, not mixing. Okay, so unmixed. Now, this flow is it mixed or unmixed? This is just one trunk of.
It's mixed.
It's mixed. This can go this can go this, mixed. Yeah, mixed. The unmixed one is, look at that. There is a temperature gradient along. Mixed one is the same, whatever. Interesting, very interesting. Anyhow, yeah, that's so you have to look at it is mixed or unmixed. One thing a little careful is you think it is mixed, but as long as this goes to here, it is not unmixed. Let me check. Let me. Well, actually, this is not very clear, but there is no gap between these two. It touches. Okay, so all I mean the fins, something like that. Do you understand? Usually, we don't let the gap here. So there is a flow. Okay, there is a this flow I'm talking about. Is that mixed or unmixed? Do you think the flow here is going to mix with this?
Unmixed.
Yeah, this is unmixed actually. It look like a mixed. No, it cannot. It goes through this way. It goes through this way. So it's unmixed as long as this one. This is a mixed, unmixed. Huh?
It's mixed.
The air goes here. It's a little go out. Do you think this is mixed with at the bottom? Answer.
It's mixed.
Still mixed. I think that there is something go out. Do you think this is gonna mix between these two? Yes or no? Mixed or unmixed? Answer again, please. Maybe you don't understand this type. Somebody answer. Mixed or unmixed? There is a offset. Otherwise, just so this, if it is not offset, is that the air goes to out? Is it mixed or unmixed? If this is, there is no offset.
That's unmixed.
If this is offset a little bit, offset, but still it follows like that. Mixed or unmixed?
It'll be mixed.
Oh my God.
It'd be unmixed.
Unmixed. How come this is mixed with the bottom of this flow? Why do you say mixed?
Well, if it's offset, I thought it would cause gaps for
Give
it to
offset, but the
separate.
gap, but only somewhere between these two, but not the bottom.
Okay, I don't understand that figure.
This air and this air is no way to mix. What's your name? Please, what's your name?
Patrick?
Patrick. So I hope you understand. This is somewhat important. Now do you understand?
Yeah, it's causing tunnels.
Now do you understand? This air
Yes, I understand.
and this gas is mixed or unmixed? The same
It's
one.
unmixed.
Yeah. Yes, unmixed. Unmixed. So a little bit you have to think about physically. Okay, mixed. I mean, otherwise it's the same. But this is a very powerful analysis. Okay, what you can do is just a parallel flow. That's all I need, and then I can use effectiveness. Very complicated heat pipe, heat exchanger. It doesn't matter. Okay. So what time is it? Let me see. 4, 5. So there is all kind of effectiveness, parallel flow. We have it, and counter flow we have. You can just pick and use it. Cross flow we have. In this case, is both fluid and mixed. Use these. If C-min is unmixed, use these. If C-max is unmixed, use these. Something like that. Okay. This is actually the inverse. sometimes it bursts. So when we look at effectiveness versus NTU for parallel flow, this is a parallel flow. It depends on the CL. And look at the counterflow. Which one do you think is more effective? Can you figure out? General. Which one is more effective? Parallel flow and counterflow? Can you say something? Come on.
Counterflow.
Yes, counterflow is more. Look at that. One about 3 is about 0.7. 1, 3 is 0.5, obviously. So counterflow is better. So if you have no reason to choose which type, what do you think? Which one is better? Counterflow is better. Okay. So without mentioning counterflow. And the crossflow is very similar to the counterflow. So, but the crossflow has a beneficial geometrically, this is sometimes very beneficial. So crossflow is good, almost the same as counterflow. Okay, in general, effectiveness. That's the power of effectiveness. Without the effectiveness, no way we can compare. Now we can compare which type, which is good, even flow patterns, something like that. But always you have to figure out the distribution like that, distribution. And then delta T1, delta T2 automatically. Okay. And the typically simple geometry like pipe flow and I told you F we in this society we don't use Darcy, we only use Fanning friction factor without the saying. Okay, they don't say just F, but it should be Fanning because Darcy the thermodynamic heat transfer textbook, they use Darcy. Okay, most of they use Darcy, but I don't know why the heat exchange society they use Fanning. I don't know. Actually, I just follow society because if you don't, you have problem because all the empirical correlation experiment you have to use Fanning. Do you understand? So without the saying, laminar is a 16. Darcy is a 64. It's a big difference. Same F. This is Fanning. This is Darcy. 4 times. It's extremely careful. Now is a 16 of Fanning. So pressure, it turns out you can use this friction factor, length, hydraulic diameter, density, mean velocity, or do you remember what is the G? What is the G? Anyone? capital G, mass velocity, they use it, okay, is rho density times mean velocity. But anyhow, they can use it and then estimate. This is simple, but we will discuss more complicated heat exchanger. This is simple pressure drop. And the fouling is after years of service, there's a scale so that you can handle fouling. There's a table, say, and you can use it as long as, but the unit you have to divide by area. So it's okay. After years, tables, I think, where's the table? Yeah, fouling, yeah, table, something approximately. You can use it to estimate. It drops pressure. And overall, I think we discussed, yes or no? Yeah, we discussed this. Yes. So if you know the single fin efficiency, you can calculate overall very easily, like multiple fins. Still, we use overall, and once we have overall, then the U is you have to use fin. If it is a fin, then you have to use fin efficiency. I think double pipe. Double pipe is already we discussed. You know, is nothing. We just double pipe, hot and cold and overall. Look at that. There's no F. What is the F value for double pipe? Is 1. Look at that. Otherwise, we discussed this and this, and hydraulic diameter, equivalent diameter, Nusselt number. We discussed everything. It's just a summary here. You can NTU, CR, parallel flow, counter flow, all kind of, okay. And yeah. So I think you have a homework. You can discuss. Well, actually, where is L information is here. If L double pipe, L information is area. Look at that. You have to look at the area. Okay, this area, L information. If L is a question, then you have to look up the area. If L is given, then okay, fine. But always the area and L you can look at. I'd like to have a break about 10 minutes. I will be back. Okay. Thank you. Bye. Hi, I'm back. Let me see. Uh, yeah, let's talk about shell and tube heat exchanger. So far, fundamentals and double pipe. We can move on shell and tube heat exchanger. So this is a schematic, and the tubular flow is we know how to handle. We can calculate Reynolds number, the set number, whatever. Each tubular flow is, and then number of tubes. But the shell side is a little different compared to endless flow of double pipe. So shell side, if you look at there is a baffles and the guide flow. So something the flow is something something like that. Okay. So baffles are holding the each tubes and the guide the flow. There is a cut so that now this is pass, just one pass. Okay, one pass, and we can make multiple pass, like we have a partition, and then flow, the tubular flow goes and then out. So one shell, two pass shell and tube heat exchanger. This is, it could be, yeah. So one shell, two pass, we call shell and tube heat exchanger. This is one shell. The shell means we have a heat exchanger. We can connect to in series. Okay. So shell one, shell two. This is a multiple shell. Even shell three. So one shell, one pass. One shell, two pass. Two shell, one pass. Something like that. We can indicate type. So here, this is baffle spacing, and total length. This is length of shell and tube, and then this is the shell diameter, D of shell, and inlet, outlet, inlet. No, I'm sorry. The inlet and outlet, and T1 out. If it is a tubular flow, something like that. Okay. So 1, 2 is depend on the which one is hot. So the length tube and the number of tube, number of pass, it could be 1 or 2, and the shell inside diameter, a number of baffle, in this case, 1, 2, 3, 4 baffle. So total length 4 baffle, but the space is 1, 2, 3, 4, 5. So one more. That's why length, number of baffle plus 1, that is a baffle spacing. And the layout, there are a number of, but typically square and rectangle. The square is unit. In case of shell type, the unit, then how many unit? Interesting is each unit has one quarter, one tube, each unit. Again, triangular actually, but the two triangular, if you look at it, only one tube. So this is a unit. This is a unit area. So, and then how many unit? So basically, we look at the unit shell, and then how many shells. Okay, something like that. So it's and then equivalent diameter, we know that triangular, there is some suggestion you can use it. The complicate is a cross-sectional area. This is very complicated of shell side. Tubular is, you know that cross flow. You know that cross flow is n number of tube times, you know that. And then each tube area. But the I mean what is pi r square? Am I right? Each tube, so that you can compute the tubular. This is tubular, but the shell side is complicated. So use shell side is ds and ct, baffle spacing, pt. What is a ct? pt is I think pt is a pitch from center to center. CT is a clearance top to bottom. CT clearance and PT. So once you do that CT and PT, then you can use compute the cross flow area. Okay. And diameter ratio, sometimes they use it, D over R, don't bother DO, DI. Okay. Outside, inside. The tube, there is a thickness, the tube. So this is DI, this is DO. So some they try to describe the tube using the diameter ratio. Don't bother. And the PR also is the PT over DI. As long as you define, you can use it. And the CT is obviously clearance and the tube P. And number of tube is, look at that. Each tube no, not each tube. The shell area inside the diameter, shell inside divided by shaded area. How many unit? How many actually unit cell, then total true. But there is some CPT is effect of H. Is there any clear figure? There's no. The CPT is, for example, this is DS, and then there is a true. There's some effect of H. So CPT take care of that. That the CPT is depend on the pass, one pass, two pass, and three pass. So just approximately, we can use the CPT. So at that path. Okay. So once we have that, otherwise, fundamental. Look at that. The fundamental equations: hot, cold, and the heat transfer area is pi inner side di times L times the number of joule. Outside is pi outside L and T, something like that. So again, the overall the same. In this case, they use cylindrical and Reynolds number, tube side, laminar flow, turbulent flow, friction factor, cross flow area. The Reynolds number, I think something, NTU, CL, and effectiveness. Otherwise, the same. You can use it. Okay, very similar. I think here example you have to go over because of sizing. There are not many books talk about sizing, but here in the beginning property, we don't know outlet. We don't know outlet. You have to assume it. Inlet is given. Outlet is assumed, and then get the property. For exam, just the one assumption is fine. But practically, if you assume it, and then finally you get the temperature outlet, it is too far, then you have to repeat calculation. So you got the density, specific heat, the thermal conductivity, viscosity, Prandtl number, and then wall. This is wall material. If it is a chromium alloy, it depends on the wall material and temperature. Okay, I is given usually inlet. One is hot, always. Two is cold. And mass flow rate, if it is given, and the fouling factor in this case given, then you can use it. If it is not, assume new. There is no fouling factor. But if it is given, you can calculate. Okay, the design is outlet temperature we design, then size. This is quite different. Outlet, we like to, this is a requirement, and pressure drop requirement, and then sizing. So if once you don't know the size, very difficult. Okay, so what I developed is wait a minute. This is Mescat. Wait a minute. We don't have a MathCAD available in this semester. So I don't think we can sizing problem. No, I don't think so. Because once you have a MathCAD, you can assume just assume and develop. Okay. Once you complete the development, the idea, complete the development, and see the pressure, temperature, outlet temperature. What is the outlet temperature? Yeah. If outlet temperature is not satisfied, you have to repeat changing the initial value, the value, size, some changing. Once you have a MathCAD developed, if you're changing 1 second, you get the result. So a couple of times you can see, but the iteration by hand, it takes hours. So you cannot design it actually by hand. You need a MathCAD. But one iteration. Do you understand? But that's not a good value. One iteration and complete. So sizing is not possible in this case. I will change. What you can do is I can provide dimensions, then calculate the rating only. Rating only in this course. No sizing, impossible without the MathCAD. Do you understand? So anyhow, the everything, I think what was homework, I forgot. Weird. Homework 4.6. No, they used the MathCAD 4.6. No way. Okay. So you cannot do. I have to. I have to change. What time is it? I'm gonna skip this part. No heat exchanger. No plate. I like to move on the pressure. Sorry about that. Yes. Pressure drop for section. I like to move on. Well, actually, I'm gonna skip the shell and tube heat exchanger. It's okay. That was a kind of fundamental I wanted. I can skip that. I'd like to move on. Pressure drop core. So suppose this is heat exchanger core. Let me see. The core, the flow come in, and then it is contracted, contraction and expansion. Look at that, the flow along the core. So that affect the pressure drop as actually, okay. So we develop the this is unit flow. It can be as many as a flow channel, a unit channel flow, and develop. So we developed. It turns out very smart, and this is final. Actually, you can just use this final. So final pressure drop, if you look at the entrance effect and the exit effect. So entrance, they use a coefficient K of C, contraction coefficient, and expansion coefficient. Sigma is, I think, porosity. Density I is inlet, density O is outlet. The complication is the gas. The fluid is much easier. The gas, the density changes, pressure changes, density changes depend on the temperature. That's why very complicate the gas heat exchanger, the pressure drop also. So we understand the Z, density inlet, porosity, easy to calculate, and then contraction, expansion is Case and London developed the graph. I'm going to talk about it. Otherwise, we know FLDH mean. As long as we density mean, we can figure out. So density mean, I think we figure out. Yes, mean. Mean is just average. Inverse of mean is in, out, and half. That's what we call mean. So you can calculate mean density, no problem. All we need is a contraction, expansion coefficient. Let's look at it. Case and London developed. This is Case and London graph. The Case and London provided the graph, then I have problem. I need the equation rather than the graph, because the graph is human reading required. Then I cannot, computer program iteration. One iteration, it usually takes 2 hours. I told you, I gave up sizing with iteration. No, because I need the program. 2 hours at least, one iteration. Okay. Again, this graph, human, even program, but still human can read it each time iteration, then trouble. So what I did actually from Case and London graph, I developed equation. Now we have a equation is available. Okay, that's the big difference. My book, I developed KE and KC for square channel, round circular channel, like Cage and London, they did it, and flat plate, and triangular, rectangular. This is circular. So we have equations. Look at that. KC, for example, square. And let me see, KD. Yeah, in terms of KD. So KE, KC in terms of KD. KD depend on the type of channel. So that I developed. So you can get the KC, KE once you have a KD. Circular channel, KD, KC is given, and something like that. So we have equations, square, we have a KD, KC. Okay, so you don't have to read, you just use flat and triangular channel and something like that. Okay, so you can handle that. Okay, for example, this is an example. This is example. Yeah, example. We like to compute the pressure drop. This is a circular. And then there is an example. You can go over, actually. Go over. All we need is look at that. KC and KE. And then we're able to calculate. Okay. So homework problem. I think now what I'm gonna do is I'm gonna change homework 4:10 and 4:11. Yeah, that's because I skipped the 4:6. And if you couldn't finish the previous homework, please, I will accept the late homework. Please do that, okay? I don't know. Let me check. Are you working on the homework? Well, this is due today. Yes, this is fine. 29:30, fine. Yeah, looks good. Yes. Yeah, thank you. You are doing very good homework. Okay. So next homework is just a 2 homework problem due next hour. I think it should be very good. And then I will discuss once you have a pressure, where is it? Pressure drop. I will discuss this one. I will discuss this one. And I will discuss not the program. I cannot handle program and this type. So you look at it. I think I have to give just 1 second. Usually I give a challenging, but oh my, 1 second. Where is my book? What? Okay, I think that's it. Yeah, I cannot do more than that. 410 and 411. Any question? I'm done. Okay, see you next hour. Thank you. Bye for your attention.